So this is my entry to the 2018 Flashing Light Prize. This is a prize for you annually making a light flash in a crazy, ingenious or humorous way. So exactly which category this monstrosity falls into, good question. So this year it's to flash a neon bulb at 1 Hz with a 50% duty cycle, so it spends half second on, half second off and alternates. And in fact in this design you get 2 just here. You can see that they spend half second on, half second off. And that should be relatively precise because of the way this works. It's based on a ring counter arrangement, so there are in fact 2 ring counters, one feeding the second. But we'll get into how it works in a moment. Usual warning about playing with high voltage, don't stick your tongue on it. In general, if you don't know what you're doing, don't do it. Like this Widowmaker here is live mains. So not the best idea, but if you know what you're doing, you'll be fine. So there are in fact 2 ring counters. This top one here is a 30 stage and takes the 60 Hz half-wave rectified mains in and divides by 30 so that the lights flash twice a second, and it just shoots round in a ring, feedbacking through this wire here. This then is coupled to a second ring counter which is just 2 stage, so that's divided by 2, takes the 2 Hz signal in, you get 1 Hz out, and they spend equal amount of time on and off. So relatively simple, but very, very pernickety to build, for reasons I'll explain after I explain how ring counter works, if you get that far in the video. This black blob here is what couples them. I couldn't get them to couple electronically. The ring counters are just too finicky with, at least with these neon bulbs. So it's in fact a neon bulb taped to a light dependent resistor. So what happens is this top one is fed half-wave rectified mains through these resistors here, goes through neons and ring counts. Then this board here, one with the actual lights that are flashing as they're meant to, is fed full just rectified mains, 170 volt DC, goes through these resistors and then through this. However, when this neon in the 30 stage ring counter fires, it causes the resistance of the light dependent resistor to go low and pulls the power just here, which these are drawing, down below their holding voltage, meaning that they extinguish. And then when this neon here goes dark, the resistance comes back up, the voltage here rises, and the other one lights. And this, as long as lighting levels are good and the phase of the moon is right, will run for quite a long time. You can see that there's clusters of resistors everywhere. These are largely because this was very, very fiddly to get going, and just added and removed them until it worked. So now to how it works. So they have a strike voltage and holding voltage, so this is the voltage drop across them. So for these bulbs, the strike is approximately 90 volts and they hold at around 70. So if you just give 80 volts to a bare bulb, like this, doesn't light. High resistance, like no current passes. You up the voltage above 90, so say 100 volts, it strikes, it lights up. That voltage can then fall back down below the 90 volt striking voltage, say 80 here, and it will remain lit all the way down to the holding voltage. When it drops below holding voltage, the bulb extinguishes, current ceases to flow. So it's this hysteresis that the ring counter uses, and what allows you to use neon bulbs almost as logic here, and avoid any silicon in this design at all. And this is a sort of simplified circuit diagram, so this would be a 5-stage counter. I have one 30-stage counter and one 2-stage counter to get the divide by 60 to get the mains frequency down to 1 Hz. So supply voltage is fed in through a relatively large valued resistor, and then the neons are in parallel, and each one then has a diode, has another smaller resistor, and then it goes to the return voltage. But between each one there's this coupling capacitor, coupling from after the diode of the first to before of the second. So what happens is when you first turn it on, voltage comes high here, they all see the higher voltage, so around 170 volts peak, although the actual voltage neon sees gets clamped before then, and one of them, whichever has the lowest striking voltage, will fire. Say this one. So this one lights up, and that clamps down this voltage along this rail to the holding voltage. The rest of them can't light. Goes through here, then there's a second voltage drop on this resistor which charges this capacitor. Now this voltage on this rail is interrupted. In the 30-stage counter, that's because it's half-wave rectified, so half the cycle it doesn't see any voltage at all. In the second 2-stage counter, it was because the LDR had pulled that rail down below the holding voltage, so these bulbs all extinguish. So this one was on. We'll call it 1. Now the voltage comes back, and they all see it again. But this time, this capacitor is still charged, it's held its charge. So this one is actually seeing a slightly higher voltage, according to the amount of voltage that was dropped over this resistor, than the rest, because there's a slight negative voltage just here. That means that this one sees a larger potential and fires first, and clamps down this voltage to the holding voltage. So now 2 lights. And this capacitor discharges, this one charges up. You can see where this goes. Voltage gets interrupted again, they all extinguish. This time the negative voltage is just here on this one, and 3 lights, and so on. It gets to the end, and then it feeds back to the beginning, and just loops round and round. It's a ring counter. Very simple. However, these are actually fairly unpleasant to build, because historically they had neon tubes that were designed for this. They had a nice big difference between the holding voltage and the strike voltage. They were also very repeatable. These neons, these are cheap imports from China. I don't know if other neons are better, but they have a very wide range of both, and they can interfere. So say, the general problem is, if you imagine that 3 goes, and imagine this one has a really high striking voltage. So you only have, what, about a tenth of the supply voltage, so about 20 volts just here, 15, 20. Pull it down. If this one's striking voltage is 15, 20 volts lower than this one will strike again, and you just get this centre bit will run again and again. The striking voltage is also dependent on ambient light level, depending on temperature, depending on how long it's been running. So it will run for about 10 minutes before it starts running into problems, but it eventually does become unstable. And that's just because these are neon indicator lamps, they're not designed for what I'm doing with them. Likewise, you should be able to sort of tap off just here to feed the next stage. So, you'd have a tap going to the next stage of neon counter. I couldn't make that work. Hence I built a sort of slightly monstrous opto-isolator using a LDR. So instead of tapping off here, what I actually have is a light dependent resistor coming off this one, similar to a homemade optical coupler. That was difficult as well because the strike voltage is dependent on ambient light levels. I had to try a great many bulbs before I found one that had the correctly lowered strike voltage in the dark to run when these ones are all running in the light. But eventually got it working, and so I have something which will flash a neon bulb at 1 Hz with 50% duty cycle, and which uses no silicon. So yes, that's my entry. Obviously not entirely silicon free, there are the diodes, but the actual meat of the counting and frequency is based on the mains and then dividing that frequency using the neon bulbs. So a slightly different entry, definitely not the simplest way of doing this, definitely not the most stable or sensible, but an interesting circuit from the past. So, thank you for watching. And of course there will be details of this competition in the description.